Okay, so we are given this transfer function g of s equal to 5 divided by 2s plus 5, and we are giving some system requirements that we'd like to satisfy. The first thing we want to satisfy is that we want a steady state error less than 0.01 due to a ramp input, right? And we want a phase margin that is larger than 40 degrees. And we would like to satisfy these requirements by first designing a lead compensator, and then later on we will do a lag compensator to match the same requirements. So let me remove this. So first of all, let's satisfy the steady state error requirements to begin with. And notice that we're talking about a ramp input here, which means that we will have to add a root at or a pole at s equal to 0, an integrator basically, in order to get finite ramp input steady state error. So that's what we do, right? That's the 1 over s here. And so if we compute the steady state, first we compute the closed loop transfer function, right? And then we compute the limit of the steady state error due to a ramp input, right? ESS is equal to S times EFS, and EFS is equal to R of S times 1 minus TFS. And so when we substitute, you will get ESS is going to be equal to 1 over K, where K is the gain that we're looking for. And we could have got this by looking at, basically by looking on the formula of the velocity constant of the system. Either way, we have that the steady state requirement that ESS is less than or equal to 0.01 gives us that K has to be bigger than 100. And so we can just pick that K equal to 100. Okay, this gives us the gain requirement. And so the new transfer function that we will be trying to design the lead for is g of s equal to 500 divided by s divided by 2 of s plus 5. All right. Next, the next step is basically to determine the phase margin that we already have for the uncompensated system, so that we would know how much phase do we need to add in for the system. Recall how we compute the phase margin. The phase margin is again the phase of the system at the gain when the gain is equal to, or the difference between the phase of the system and negative 180 degrees when the gain of the system is equal to 1. And so we put the gain of the system equal to 1 and we solve for omega. This will give us this fourth order equation. We can do, you can solve this equation however you want. Recall that in the lecture, Dr. Marco solved the equation using Newton iterations, right? Either way, he will get that the frequency is going to be 15.7 radians per second. This is the crossover frequency. Now we compute the phase at that frequency. So the phase of this transfer function is just the phase of its factors. We have negative 90, that's the phase of the pole at the origin, and then the phase of the first order pole. That will be negative 90 minus 81 degrees, so a total of negative 171 degrees. Someone has a question? No? Okay. And so if we want to compute the phase margin is just 180 minus 171, we get 9 degrees. So that so these 9 degrees are basically the phase margin of the uncompensated system, which means that if we want to get a phase margin larger than 40 degrees, we need to add this much, like 40 minus 9 degrees, and we also had some, we also add some safety factor, which about 40 degrees, so that the sum or the total phase that we need to add eventually is going to be 45 degrees. And we want to add that at omega at omega c, so that the phase margin becomes equal to or becomes larger than 40 degrees, right? So the third step in the process is basically that we would like to determine alpha and the pole and zero locations. So recall that this is how we parameterized our lead controller after we picked the gain to satisfy the steady state error requirements. So we have two constants here to look for, alpha and tau, right? Now, here you are. Then recall the formula that we used to find to find alpha, right? We want to add a phase of 45 degrees. This will give us, if we solve this equation, this will give us that alpha will be approximately 5.81, which we will take to be 6, just to make things simpler, and also to add some margin of safety. And so because we add the maximum phase at omega equal to c, we are going to set the geometric mean of the pole and the zero to be equal to omega c, so that we add the maximum phase by adding the lead compensator, so that we add the omega c. So we set omega m to be equal to 15.71. Now, the rest is just basically solving for alpha, like solving for tau. We already have alpha, right? So we solve for tau. We know that the geometric mean is basically omega n is equal to 1 over square root of alpha times tau, right? And so this tells us that tau is approximately, or is going to be equal to 0.026. So now we have tau and alpha. This means that we have our compensators, right? We have the gain from previously to satisfy the steady state requirements, that's 100. And then we have alpha times tau, and tau, this gives us the compensator. Now we need to check if these requirements are met. Let me quickly go to Matlab. No. Do you see my screen, guys?
Yep, we do.
So the original transfer function was 5 divided by 2 times s plus 5. And then we added the steady state error, right? So now we have g is going to be equal to 100 divided by s times g. And we designed a lead compensator. Let's call it lead. And that was 1 plus 6 times 0.026 times s divided by 1 plus 4.026 times s. Okay, so let's see. First of all, let's compute the closed loop system, which is basically feedback of g lead times g. And also let's look at the Bode diagram of G lead times G. Let's call this figure 1 and figure 2. Let's have a look at the step of, or yeah, so we have the impulse of 1 over s square minus 1 over s squared times t. So can someone tell me what is this? What I just highlighted? 1 over s squared minus 1 over s squared times t. Any ideas?
Is that the error?
Yeah, exactly. That's the error. Yeah, that's EFS. So I want to have a look at what happens to EFS as time goes through. Or just basically want to look at the steady state error. So we run this, and here we are. Also add just the traditional function, and we call this space 0.1, 2. So this line basically just tells us the range of frequencies that we are interested in looking at the Bode plot for. So I'm interested in just looking at 10 to the power 0.1, which is 0.1, and 10 to the power 2, which is 100, right? And I'm just going to take 1,000 points between them so that the plot is accurate in between them. All right. So here are the two systems. This system is okay. So the system in blue, this is G, right? This is the uncompensated system, and the system in red is the compensated system. So if we look at the stability margins, we see that that the original system had a phase margin of 9 degrees, whereas the compensated system has a phase margin of 44.1 degrees, which is larger than 40. So we satisfied the desired requirements. We noticed that the omega c was shifted again because was shifted like higher, and that's what we expect from a lead compensator, if you recall from the lecture. And if we look at the steady state error requirements, we see that we don't have the steady state yet. Yeah. Anyways, we see that the steady state error approaches 0.01 as time goes to infinity. All right. Any questions? Okay. So this is the first problem we have today. The second problem is that we would like to satisfy the same requirements, but now instead of using a lag compensator, a lead compensator, we're going to use a lag compensator. Okay. And so the steady state error requirements are not going to be changed. So we can just use the same steady state error requirements, which basically tell us that the transfer function is going to be 100 divided by s times the original function, which is going to be 500 divided by s times 2s plus 5. We would like a phase requirement bigger than 40 degrees. So so let's say that we want a phase requirement that is larger than or that is equal to 55 degrees. Again, we added a safety margin so that we can achieve what we want. And so to design a lag compensator, what happens is that instead of adding phase, we kind of pull the magnitude plot or like, okay, so the lead compensator, what happens is that we add a certain amount of phase at omega, at omega c, right? So we don't try to actively change omega c. It changes, but not that we're trying to actively do that. Instead, what we want to do is that to add a certain amount of phase at the previous omega c in order to satisfy the phase requirement. In the lag compensator, however, instead of modifying the phase plot, we modify the the gain plot, and basically we pull the gain plot down so that or basically we change omega c from a certain number to another number. So so the first step is basically looking or choosing the phase margin that we want to achieve. The second step is looking where is the phase margin, or where is the phase of the system, the difference between the phase of the system and negative 180 degrees equal to 55 degrees. So if we look on the Bode plot, let me go back to the screen. So if we look at Bode of G and W, if we look at the system, we see that the phase, or the difference between the phase of the system and negative 180 degrees is achieved at a frequency of approximately 1.75. Okay, at this frequency, the system has a phase of negative 125 degrees, which means that we have a phase of about 55 degrees here, or a phase margin of 55 degrees, right? So instead of adding a certain amount of phase at omega c, what we're going to do is that we are going to shift omega c from this value, which is 15.7. Instead, we want omega c to be equal to, or to bring omega c all over 1.75, okay? In other words, we need to add an attenuation of about this much, which is 33.4 decibels. We want to add this much attenuation so that the gain plot of the system drops down to 0, right, at this particular frequency, 1.75. And then we hope to do that without affecting the phase plot as uh, a lot, right? Okay, and so that's what we do in the phase or in the lag design. First, we go to first we look at how much attenuation we need to have. So we said that we would like approximately 33.5. So for safety, we're just going to make that 34. Okay. And then recall that the amount of attenuation is equal to 20 times log alpha. So 20 times log alpha, we want that to be equal to negative 34, which means that this will give us that alpha is approximately equal to 0.02. Now we have alpha. The next step is basically to use this alpha to compute the the pole and zero locations. And so recall the rule that Dr. Marco said in the lectures, which is basically we are going to set set the location of the zero to be this is the value, or the dominant pole location for the original system, right? So that adding a pole or a zero does not affect the behavior of the system too much. This will give us, or like if we want to set the zero at this, uh, uh, um, if the pole of the system is at 2.5, right, because we have 2s plus 5. So if the pole is at 2.5, we divide by 50. That will give us that the zero will be at 0.05. And recall that the zero is equal to, so let me erase this, right? Omega z is equal to 1 over tau alpha. So this basically means that tau is equal to 1 over alpha omega z, which when we compute it is going to be equal to 1000. So now we have tau, and we know that the zero is going to be equal to at 2.05, which means that the lead compensator is going to have this form 1 plus 20s divided by 1000s. So we see that this pole is at 0.0001, which is very close to the origin, right? So we hope, and this one also is very close to the origin, so that means that they are not going to affect the behavior, or they are not going to affect the phase of the system, as you recall from our earlier discussions about the root locus, or about the lag design for a system for a lag design using root locus, right? If the pole and the zero of the compensator are close to the origin, they are not going to change the phase plot as much. And so let's go and check what happens using that compensator. So let's call this one G lag, and is equal to 1 plus 20 times S divided by 1 plus 1000 times S. Again, same thing, just gonna run the same. And instead of this, do that. This is the lag. Okay, this is the lag. So this is the steady state error. We see that it started, it decays much, in a much slower pace, but it eventually reaches 0.01. Can someone tell me why does it decay that very slowly? Any ideas? What is the difference between the lead compensator that we added and the lag compensator? Any wild guesses? Just anything. Okay, so when we added in the when we added the lag compensator, the pole and the zero that we added are very close to the origin, right? Which means that they do what? They dominate the response of the system, right? And so if you have a pole that is very close to the origin, it will have a decay rate that is very small, right? And so it will keep going on forever. Like it will persist forever, right? And so that's why we see this steady state response. It's going to take a long time in order to settle down. Okay, if we look at the pole zero map of T, if you look at the pole zero map of the closed loop system with the lag, you see that we have a pole and a zero here at, so let's try to zoom a little bit here. We have a pole, or we have a zero at 0.05 and a pole at negative 0.05, right? Which, again, this pole is going to dominate the behavior of the system. We will have a very long settling time. Okay, let me go back to the Bode plots, right? So these are the Bode plots of the compensated and the uncompensated system. Can someone tell me, just from looking at these Bode diagrams, which one is the compensated and which one is the uncompensated system?
The red one is the compensated one.
Why?
Because you lowered the critical frequency.
Exactly. That's exactly what we did by adding the lag compensator, right? We pulled the magnitude down by adding a certain amount of attenuation, and we see that the effect on the phase is almost negligible, right? Because um, we placed the zero and the pole very close to the origin, so that their effect on higher frequency or on the phase of higher frequencies is negligible. So now, if we look at the stability margins, we see that the original omega crossing was about 15.7, whereas the new omega crossing is about 1.66, which is close to the value that we wanted to achieve. And we see that the phase margin was originally 9 degrees as we computed, but the new phase margin is 54 degrees, which is larger than the 40 that was part of the requirements, and so we satisfied the transit requirements. Now, as a final comparison, let's just look at the Bode diagram of G underscore lead times G, then G times G lag times G and W. So these are the three systems. We see that the lead compensator significantly changes the phase diagram, right? Without affecting the gain diagram as much, whereas the lag compensator affects the gain diagram without affecting the phase diagram too much. If we look at stability margins, we see that the lead compensator changed the crossing frequency, right? Because it did affect the gain margin a little bit, but not as much as it affects the phase, right? So we have an increase. Okay, the phase, the gain, the omega c basically more or less doubled, whereas the phase, we have an increase of the phase from 9 degrees to 4 degrees, right? So we have a quadruple increase in the phase, whereas in the case of the lag compensator, we have that like the gain did not change much, right? It's almost, or I'm sorry, the phase did not change much. It's almost the same, whereas we have a significant decrease in omega c from 15.7 to approximately 1.65. So this concludes the problem 3 in the final homework set, I think. Um, let's see. So this is problem 3, right? Yeah. So we design a phase lead. So we designed a phase lead, we designed a phase lag, and we checked the Matlab um, requirements. Okay, so does anyone have any questions? All right, that will be it for this discussion, and I think that will be our last discussion for this quarter. Thank you guys for your attention, and good luck in your finals. So let me ask you quickly. Does anyone know where when the final is?
It's on Monday. I don't know. I don't remember what time.
So Monday the next week, right? So okay, so that's good. So I'm probably gonna add an extra office hour tomorrow, Thursday, and I'll be available um, in my office hours on Friday at 1 p.m. as usual. I think most likely the exam will be later in the day so that everyone, so that people from other time zones as well will be able to make it. So, um, so I think I might even add another office hour on Monday or something, but I'll just write an announcement later today. So thank you guys and good luck.
Thank you, Mahmood.
Thank you.
You're welcome.